Good morning, everyone. We'll start in a few moments. In the meantime, if you want to prepare for what we're about to do, we'll take a look at example 33.3 on page 1447 of your textbook, in which we'll practice to find the binding energy of a given nucleus. So, last time we saw each other yesterday, after wrapping up quantum mechanics, we started our study of nuclear physics, which is the study of the physics of the nucleus of an atom. We saw that there was some binding energy which bound the protons and neutrons, collectively known as the nucleons, together, despite the electromagnetic repulsion. And this binding energy came from a difference in the mass between what we would get from just adding that of all of its components versus that of the actual nucleus. So the two masses doesn't match. There is a difference between the two, which creates the binding energy we're about to see from the mass energy equivalence. Mass is just another form of energy. As long as the total energy is conserved, mass counted in it, everything is fine. So, in example 43.3, we'll take a look at a given nucleon of nickel 62. Would it be possible to use a darker pen? I'll probably switch sheet. If I have to use another pen, I won't be able to use the other side of the sheet. So example 43.3, in which we'll study nickel 62, was it? Yep, 62 nucleons. Nickel is defined as having 28 protons. No problem, John. Thanks for pointing it out. We want to find the mass defect, the total binding energy, and the binding energy per nucleon of this nucleus. And we are told what its actual mass is in terms of the atomic mass unit. So we are told that its mass, already down as mass nickel 62, is equal to 61.928 345 times U. So what we'll do first, well, they asked us to find each quantity separated. So we'll start with the mass defect. So the mass defect is the difference between the masses of all of the components versus that of the actual nucleus. And it was given by Z, the number of protons, times the mass of an hydrogen atom, plus the number of neutrons. So we know that we have 62 nucleons, 28 of them are protons, so the difference will be the number of neutrons. You can also find it in advance and then just plug in the number. Here, I'll just put the difference to explain what I'm doing. Times the mass of a neutron. So these are the components, and we subtract the mass of the actual nucleus, which is 61. I write the symbol for now. So this is the mass defect. For now, I'll just write it in units of U. So some number times U. So for this, I'll have to go and find all of the masses I need. So for hydrogen, I'll go in. You can go either on the table I put up on layout, or you should have it in your textbook in table 43.2. So we have hydrogen with a single proton, no neutron in it. So we are told that its atomic mass is 1.007825 times U. 62 minus 28, 34. Times the mass of a neutron, also in units of U. For this, you can either use the values in kilogram and divide it by U. You also have it at the bottom of page 1441. In fact, you have the proton, the neutron, and the electron. So we are told that a neutron has a mass of 1.008. 0.008 665 times U. And next, the mass of this, 61.928,395 times U. So I'll put all the U's towards the right and just find all of the factors in front. So I have 28 times 1.007825 plus 34 times 1.008665 minus 61.928395, which gives me, with all of the numbers, 0.585315. All of this times U. I'll keep it like this, since it'll be easier to find the energy in a few moments. Next, we want to find the total binding energy. So the binding energy is related to the mass defect through the relation we had last time. Binding relation is the mass defect times c squared. So it'll be R number times U times c squared. And this, we know as having a numerical value. This is 931.5 mega electron volts. So 10 to the power 6 electron volts. So this is why we always try to factor U to combine it with the c squared, since we have already a value for it. So through this, EB, the binding energy, will be equal to R number times 931.5, which gives us 545.22 approximately mega electron volts. So this is the total binding energy of all of the nucleus. Sometimes, to figure out if the nucleus is stable or not, it might be more useful to find the binding energy for each nucleon on average. So we'll just take this value and divide it by 8, the number of nucleon, 62. So per nucleon, EB over 8. So R value over 62. This is 66, I meant 62. In mega electron volts. So on average, each nucleon is bound to its neighbors through a binding energy of 8.794, let's say, mega electron volts. Did I make a mistake? No, should be fine. All right. So to find the binding energy, you'll have to find the mass of hydrogen absolutely, of a neutron absolutely, and plug in the value of the actual nucleus you are taking a look at. Take the difference between the mass of the components and the mass of the total nucleus, which will give you the mass defect, and then you multiply it by c squared to find the binding energy. If you are tasked with finding the binding energy per nucleon, just divide it by 8, the number of nucleon inside of the nucleus. So on this, do you have some questions, some comments, anything? Otherwise, on today's menu, we'll continue to study radioactivity as well as nuclear reaction. So we found out a way to find the binding energy of a given nucleus. Some are more stable than others, which is represented by having a larger binding energy per nucleon, and so they will decay after some time if they are unstable. So this decay will take the form of radioactivity, of which we'll study a total of 4 different forms. And unlike what is shown here, I won't directly go into decay rate. We'll jump over it and take a look at a quick look at fission and fusion, the 2 main types of nuclear reaction. So for today's class, I expect it to last for about an hour. So next Monday, what we still have to cover would be the decay rate, for which I would expect to take an hour, and then afterwards we just have to do the summary for the 3rd exam. So for today, we'll mainly focus on different type of nuclear reaction and decay, as well as the energy associated with them. So I'll just do I need to? I don't think I need to change my setup. I'll try to keep it as is. If I find the need to switch the camera, I'll just take a short 3 minutes break and to change it up. So I just need to fetch my keyboard, put away the book. Tomorrow I'll be available to answer your questions as usual during on Wednesdays. Also, after we're done today, I'll also be available until the end of the scheduled class So I'll be on Zoom. I was thinking maybe tomorrow from 1 to 2. But yeah, for actual theory, no new theory for tomorrow. Actually, after we're done today, we'll say we'll already have done 3 hours this week. Radioactivity was the process through which some nuclei will start from an unstable configuration and try to jump to a more stable one. So depending on what their initial configuration is, what their initial number of protons, number of neutrons is, they may need to lose some neutrons or lose some protons. They might need to do a little bit of both. So there will be a bunch of processes through which you'll be able to change their configuration and try to reach a more stable one. The first one we'll take a look at, first, my bad. General nuclear reaction, what is the logic to find the energy that is going on in a nuclear reaction? This will apply to every type of decay as well as for fission and fusion. This is the general principle. So the energy that you will either get or need to start a nuclear reaction is found through the very same principle that we deduced the form of the binding energy. It is again given by a difference between the mass that we have between two masses. Here, instead of being the difference between the mass of all of the components and the nucleus as we had for the binding energy, instead it will be different the masses of what we have before the reaction and what we have after. So I wrote down here delta M. So we use the same symbol since again it is the difference between two masses, but here we won't call it the mass defect. It is the initial mass minus the final mass. So that if after the reaction the mass we have at the end is smaller than that we had in the beginning, that means that to compensate we have to release some energy. We need some additional energy at the end for the total energy, which also encompasses the mass to balance. And if instead we end up with something that is more massive at the end than what we had at the beginning, we'll need to throw some energy at the system at the beginning in order to create this additional mass. So this will reflect into a difference of sign for the energy associated with the reaction Q. And its sign will differentiate between do we need to give the energy to the system, which will be an endothermal, depending on the word you're used to, reaction, or do we get energy at the end? Do we end up with a smaller mass, so do we have additional energy at the end? Do we have an exothermic reaction? So this will be reflected in the sign of the nuclear reaction. And it will also give us an indication of if the reaction can happen on its own without any external intervention. Our criteria will be if we need to give energy to the system for the reaction to be possible, it won't be able to happen on its own. We need something to give it energy, so it won't be able to happen spontaneously. So if it is exothermic, fine, it can happen on its own in nature. But if it is endothermic, it cannot happen on its own. In the textbook, they also use a criteria based on mass. This is the same thing because whether the reaction is exothermic or endothermic depends on if we have a heavier or lighter product than the reactants. And the notation we'll use to describe a nuclear reaction is very similar to that you have used in chemistry so far. We'll just have some type of equation with an arrow separating the reactants from the products. The products are on the right, reactants on are on the left. And if we wanted to add the energy to it, we would put it here on the right, so that if it is positive, it is indeed on the right. If it is negative, that means we need to input it on the left. So this will be the general logic behind all of the expressions we'll introduce for the energy released in all the specific types of decay. The first one to take a look at will be called alpha decay. So it releases, as its name implies, an alpha particle, which is the same particle you have used a few times in electricity and magnetism. It is a nucleus of helium-4. So it is made up of 2 protons and 2 neutrons. So whenever it is produced, we have some initial nucleus, and after having the decay, we have the alpha particle, the helium-4 nucleus, and we'll have some other nucleus which will be produced through this reaction. So since we released an alpha particle which has 2 protons and 2 neutrons, this nucleus has 2 less protons than what we started with. So I presented it with, here if I write it as having Z protons, this one has Z minus 2. And it has a helium-4 nucleus has a total of 4 nucleons, 2 protons, 2 neutrons. So the total number of nucleons, 8, will be reduced by a factor of 4 in the products we have. So in the nuclear reactions and all of the types of decay we'll study, the element won't stay the same. Through nuclear reaction, we can actually create new elements from others. So it might seem a bit like alchemy, but it is not. And the energy associated with the reaction is given through the principle introduced. First, what do we have? We have an atom of this element, which I represented as mx. We'll already start following the number of electrons. This will be important in the 2 next type of decays. This one will balance on its own, so not so bad. The 2 next will have to follow them in order to explain the expression. So here, let's say I start with a neutral atom of element X, which has Z proton and thus Z electrons also. After the reaction, the nucleus has been split, but I still have the Z total electrons. For Y to be stable, not to be stable, to be neutral, sorry, I need Z minus 2. And for the alpha particle to be neutral, I need 2. So I need a total of Z here to be neutral. I need a total of Z here to be neutral. So all of the electrons will already be counted inside of the masses of these. So we won't have to add another term for the electrons. This will change in the next parts. So here we have the mass of the neutral atom of element X that we had before, minus what we have at the end, a neutral atom of Y and a neutral atom of helium-4. In all of the expressions, whenever we have an M, it will always be of a neutral atom, because this is what we have access to in the literature. This is not the only type of decay. So one thing I had to say. So an alpha particle, since it is a helium-4 nucleus, it tends to be quite heavy. So in general, these type of particles, this type of decay won't produce particles that go very far. It will tend to collide with a lot of particles and stop in their tracks pretty quick. However, if you are hit by those, they will do a lot of damage. So they are very large and very heavy particles, at least on the scale of an atom. These tend to do a lot of damage, but don't go very far. The next two will be two types of what we'll call beta decay, which we'll put a sign to them, which we'll call beta minus and beta plus. So first, in beta minus, another way through which a nucleus can change its configuration. In alpha decay, it changed both its number of neutrons and protons. In the beta decay, we change only the number of protons. In this case, we have a neutron inside of the nucleus. It will break into smaller parts. In fact, a neutron and a proton are not elementary particles. They are made up of smaller particles called quark. So they can be broken down. They can transform into something else. Like here, a neutron will transform into a proton, which will stay bound inside of the nucleus. So these two are inside of the nucleus. And also, through the conservation of charge, we started with something that was neutral. Here we have something positive. We need an equal negative charge to cancel it. So an electron will also be ejected. We call it beta minus decay because we throw out an electron which is negatively charged. Before I move on to the next part, just the next part of the formula. So for now, I'll forget about this part. I'll go back to it in a few moments. We focus just on the first part, a neutron that transforms into a proton and an electron. So if we start with an atom of element X with Z proton and A nucleons, after the reaction, well, we have the electron that was ejected. We have one more proton than we had before. So the number Z increases by 1 compared to what we had before. But the number of nucleons, since it is the total of neutrons and protons, in this reaction, we lost a neutron, but we gained the proton. So the total number stayed constant. So A stays the same. So for this reaction, we'll change element, since the element depends on the number of protons, but we'll keep the same number of nucleons, A. And for the energy either released or needed for this reaction, here we started off with a neutral atom with Z protons and so Z electrons. Here we have a nucleus of a nucleus with Z plus 1 protons, and we still have the Z electrons that this one had before, plus an extra one released. So here on the left we have Z electrons. On the right we have the Z initial ones plus the extra one for total Z plus 1. And this atom has Z plus 1 protons. So if we want to make a neutral atom out of it, we'll take all of the Z plus 1 electrons, shove them in this atom, and end up with a neutral atom of Y. So in Q, we just have the neutral atom of X at the beginning and the equivalent of a neutral atom of Y at the end. Here, the extra electron is just thrown into this to make it neutral. This is for beta minus. Here, the small thing I neglected so far is a particle that was predicted to exist, in fact, through this type of reaction, which is called a neutrino. Here, more precisely, an anti-neutrino. So the antiparticle of a neutrino, antiparticle as we discussed yesterday, as being a particle of antimatter. So it is so just short parenthesis. It's not very important. Neutrinos are particles that do not interact very strongly with matter, so they are very, very hard to detect. They generally pass through obstacles without any problem. In fact, right now, passing through you and through Earth are million, I could even say billions of neutrinos that pass through without any problems. So these have a very, 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 very small mass. So we only have been able to put an upper limit to it. We haven't even been able to find actual value for the mass of this particle. We only know that it is very, very light, and so it has a very small energy, which we neglect here in the calculation. It will maybe bring a very small correction, but not that important for the final result. It was needed because of the conservation of, well, energy to, if we want better precision, and momentum. If here we started with a particle with zero momentum, this also had zero momentum. Therefore, this to have a bunch of values of possible momentum, as was experimentally observed, we needed an extra particle. So the sum of the momentum of these two would be zero, and not just one at a time. It's just an extra particle that we needed to have the conservation of momentum, but here we won't take it into account at all in the calculations. And another process. So here was beta minus. If a neutron can change into a proton and something else, the proton will also be able to transform into other particles. A proton will be able to change into a neutron, both of these again being bound inside of the nucleus. And again, through the conservation of charge. I forgot the neutrino is not charged, so it doesn't affect the conservation of charge. Here we started with a positive charge on the left, so the right also have to be positively charged. And for this, we released a positron. So here, E plus is a positron, the antiparticle of the electron. So with the same mass, but with a positive charge instead of a negative charge. So it is an antiparticle, a particle of antimatter. So E plus does the name of the decay, beta plus. Again, if we analyze what is going on in this reaction, we started with one proton, which was changed into one neutron and a positron. So in the reaction at the end, we have the positron that was ejected out of the nucleus. We started with a nucleus with Z protons and A neutrons. In the process, one proton was destroyed. So compared to what we initially had, we have one less proton, so Z minus 1. But since, again, the number of nucleons is the total of protons and neutrons, A remains the same. We lost one proton, but gained one neutron. A remains the same. For the energy that is either released or needed for this reaction, again, we'll follow the electron cloud to see how many we need to build our neutral atoms we need in the end in our expression. So here we start with a neutral atom of X, so with Z electrons. Even when the proton separates, we still have these Z electrons around. So here we have the same Z electrons we had before. We need Z minus 1 in order to make this neutral. So after making this neutral, we still have one extra electron plus the positron that is here. And these two have the same mass. The mass of a positron is the same as the mass of the extra electron. So the energy will take the form of the neutral atom we had at the beginning, minus what we have at the end, the neutral atom of Y, and minus 2 times the mass of an electron. So you could also write it down as minus the mass of a positron minus the mass of an electron. This would be the same. Also, in general, since the positron is the antiparticle of the electron, the two will probably meet, destroy each other, and release energy in the form of a photon with this energy. So again, you'll probably detect it as a photon in the end, but still it is energy that is released. This explains the form of the energy either released or needed for this reaction. So what will determine what type of decay an atom will tend to go through? Well, it will need to be exothermic for it to happen on its own. If it is endothermic, it is not a possible decay for this nucleus. And this type of reaction, the beta plus decay, I sent you a video inside of the study guide. I highly suggest you check it out. It is used for a PET scan, positron, emission, tomography. Do I need to point at my face to do it? Yeah, I need to. Okay. Just 1 minute. It actually looks like I needed to change my setup. So what you have, what is generally done is in a lab, the doctors and scientists prepare a radioactive compound which tends to decay under a beta plus decay, injected into the patient, and thus in the patient with an agent that goes and links to the part that you want to make an image of. The compound releases positrons inside of the body. And since the body of the patient, your body as well, is made up of matter, there are a lot of electrons around. So this positron will, in the end, meet one electron of the body of the patient. They destroy each other and will send energy in the form of photons around them. In general, their momentum will tend to be around zero. So they create two photons going in the opposite directions, which are then detected on a ring outside of the patient. So this is why in this type of energy, you always put the patient inside of a huge ring inside of a machine. The ring is made up of a whole bunch of detectors, which detects the two photons. By combining the two directions, determines where they came from, and from this they can find, for instance, if the compound was made to attach itself to a tumor or something, they can detect wherever it is by finding the position from which the two photons came from. If you have a bunch of disintegrations of positrons being emitted and afterwards annihilating with an electron around them, you will have a bunch of events, a bunch of disintegration, and by combining all of the results, you can find the actual location. So the video, I really suggest you take a look at it. It's very well done, very well animated. It shows what is going on pretty well, at least in my opinion. So this is a way that we can use decays in a medical situation. And the last type of decay, which I won't take a lot of time on it. What we call a gamma decay, is just the emission of a photon. So sometimes after going through another type of decay, mostly alpha decay, the nucleus will end up in an excited state. Much like the electron has energy levels when inside of an atom, the nucleus also does. So after going through an earlier decay, might end up in an excited state, and to go back to its ground state, will emit a photon, generally with a very, very high energy, higher, greater than X-rays and so on, which we call a gamma ray. So a gamma ray. It's just a photon with a very, very large energy. So four total types of decay. Alpha decay, in which an helium-4 nucleus is ejected. Beta minus, in which an electron is ejected. Beta plus, in which we send a positron. And gamma, in which just a regular photon is sent out. On the four different types of decay, would you have some questions, something you like, some comments, objection, something you'd like us to go over once more? Otherwise, we'll try our hands at finding the energy either needed or released in a given decay. And afterwards, we'll take a quick look at fission and fusion. What are they? In what situations do they occur? So we'll take a look at example. Which one was it again? 33.6. Which I'll do in a slightly different way than the textbook does. I'll just take the sheet I had before. Oh well. So, 33.6, in which we want to find if a given nucleus can undergo beta minus decay. So in the textbook, they look at the masses. Here, I'll do it through the energy. Find if it is exothermic or endothermic, and from there, deduce if it is possible for it to decay on its own through this. So we'll take a look at Cobalt 60. So Cobalt has, from what we're told, 27 protons. Want to show if it is unstable relative to beta minus decay. So unstable relative to this decay, meaning that it will go through this decay. We're told that it has an atomic mass of 59 59.933817 times U. And in case we need it, we also reminded the mass of nickel 60, which is 59.930786 times U. So to see if it is a beta minus emitter, if it can go through beta minus decay, we'll check its energy. So in a beta minus decay, we found that the energy either needed or released was given by the mass of the initial nucleus, so cobalt 60, minus the mass of the final one. Here, actually, I do not know it yet. They told me this mass, but I don't know yet that this is the result. So I'll find it. Sorry. Where do I find it? Where do I find it? I'll do it over. I'll do it over here. So in order to find the result of a given decay, we'll have to use what we know it does on its number of protons and nucleons. So in a beta minus decay, if we start with a given element, here we have cobalt 60. If we forget about the antineutrino, sorry, we know that we have to eject. We had an electron at the end, and what happened to the other nucleus at the end? The number of nucleons stays the same. It stays at 60, and in a beta minus decay, a neutron changes into a proton, so we gain a proton. So here, if we had 27, here we'll have 27 plus 1, for a total of 28. Knowing how many protons we have at the end, we can go and find what element do we have in front of us. So for this, you can take a look, for instance, at the periodic table. You should have one in your textbook, otherwise I also put one up on Leah. On your textbook, where it is? I'm sure I saw one. Yeah, you have one on page A5, so fifth page of the annexes. It is in Appendix D. So you have a periodic table, and from there you can see that the element that has 28 protons is nickel. So from this, we can deduce that what we'll have in the end is nickel from the number of protons, which was deduced from what we knew was the effect of a beta minus decay. We gain one proton inside of the nucleus. So sometimes some numbers will only be tasked with finding the product. Sometimes, like we have to do here, in addition to this, we'll find the energy. So now I can write, without cheating, that what I'll have in the end is nickel 60. I know all of the masses. What I'll do, all of these are in units of U, so I'll just write down numbers and already factor U towards the right. So cobalt was 59.933187 minus that of nickel, 59.930786. All of this times UC squared, so times 931.5 mega electron volts. And so from this, the energy we have, let's find out, 59.933817 minus this abomination, 786 times 931.5. So I'd end up with an energy of 2.82, let's say 34 mega electron volts. This is positive. So we have an exothermic reaction. This reaction can happen on its own because it does not require any type of energy at the beginning to start. So indeed, through this, we can say that Cobalt 60 can undergo a beta minus decay in nature. So here we increased the number of protons since we had a beta minus decay. If we had been tasked with studying a beta plus decay, in a beta plus, the number of protons decreases since we destroy a proton to create a neutron. So here we would have 26 instead, 27 minus 1. In the case of an alpha decay, the number of protons would have decreased by 2 since we eject a particle with 2 protons. So we would have ended up with 25. The number of nucleons would have decreased by 4 since the alpha particle has 4 nucleons. So the product would have had 56 nucleons. So depending on the type of decay you are studying, you will have to use these rules in order to find the product that we will have in the end. That will bring us to the end of this example. The process is really the same for the other type of decay. For a general reaction, so you will have sometimes to find, for instance, the product or one of the products, look at the other components around them, find out what is missing. You have a bunch of examples I sent to you on layout. So on decays and how to find the energy and the products of a given nuclear reaction. You have some questions, comments before we have a short talk on fission and fusion. Yes, Kimberly. It is exothermic, or a positive energy from where we found it. That means that the final mass is smaller than the initial mass. Since mass is a form of energy, that means that if we only consider mass, at the end we would have a smaller amount of energy than what we started with. So to compensate, that means that some additional energy is produced at the end, so that the mass, the energy at the beginning is equal to the energy at the end. It is exothermic. In chemistry, you might have used the inverse. What is the word I'm looking for? Not conversion. The inverse convention. Since in chemistry you probably assumed that the energy was on the left side of the equation, so you assumed that you had to give it to the system. So if it was negative, that means that instead you got it out of the reaction. Here we use the opposite convention. We assume that it is on the right side of the equation. So if it is negative, that means that instead it was on the left side. So we needed to give it to the system. Negative endothermic, positive exothermic. Thank you for asking. So in the last part for today, we'll just have a talk about fusion and fission. So no nuclear fission associated with it. Just what do they mean, in what context do they occur, and why do we need them? Just go directly to fission and fusion. Fission and fusion are the two main types of nuclear reactions. So fission first is the type of reaction in which we start off with, in general, very heavy nuclei, and we break them down into smaller ones. So fission, you always start off with something large and end up with something a lot smaller. It is the first type of nuclear reaction that was done artificially by human beings. For instance, it is the one that is being used in nuclear reactors and in classical, ordinary nuclear bombs, the first type of nuclear bombs that were produced. In general, we use uranium 235 since it has the necessary properties to maintain what we call a self-sustained reaction. So a nuclear reaction that keeps going and going and going. The general principle in this type of reaction is the following. Also in the study guide, I sent you a video by Veritasium on this subject. Again, it is very, very well done. So I really suggest you go check it out. So what you have, if you consider a first nucleus of uranium 235, so this is a type of nucleus that whenever it catches a neutron, it becomes unstable and then breaks down into smaller nuclei. So what would you generally do in order to produce bombs and nuclear reaction out of this? Well, first we have to compress the material for the density to be high to maximize the chances of the reaction to keep going. We send, I forgot to draw it, a first neutron inside of the system, which is captured by a nucleus of uranium 235. And whenever it breaks down, it breaks down into smaller nuclei, but it also releases some neutrons. On average, if I remember correctly, on average, it releases 2.5 neutrons. Whenever it breaks down, it releases some new neutrons inside of the system, which themselves are captured by new nuclei, which break apart also, which release new neutrons, which go and break apart new nuclei, and so on. And if you let it go on its own, in a very, very small amount of time, you break an immensely large amount of nuclei. And through the total of each of these small reactions, release an enormous amount of energy. You have just created an atomic bomb. So an atomic bomb is a reaction in which you have a chain reaction of the breaking of one nucleus, making all of the other nuclei of the system, maybe not all of them, but the vast majority of them, breaking apart in a very small amount of time, releasing a very huge amount of energy in a small amount of time, which creates the blast of energy, and afterwards the increases in temperature, increases in pressure, and the wavefront, the wavefront that goes around the initial impact of the bomb. In a reactor, the principle is the same, except we don't want it to explode. So we keep this reaction under control by absorbing some of the neutrons. So if for instance, this nucleus, whenever it breaks apart, releases a few neutrons, we try to absorb most of them so that, on average, only one of the neutrons that is sent out is not absorbed and can break one other nucleus, which sends some other neutrons. One of them is not absorbed, which goes to break another nucleus. So we try to keep the reaction one-on-one instead of having it multiply and break a bunch of other nuclei. We do this, for instance, by putting it control rods in the system, so rods that tend to absorb neutrons without having an additional reaction, so without breaking some nuclei. The balance, as stated in the Veritasium video, is very hard to obtain. If you absorb too many, you'll just kill off the reaction. You won't continue breaking nuclei as you go, so stop producing energy. But if you do not absorb as many as needed, we'll just go back to a bomb. The balance is very hard to keep under control. And free energy, in general, we boil some water and then make some turbines rotate. So afterwards, it is the same principle as whenever you have a hydro plant or a steamed power plant. Afterwards, it's the same principle. The only difference is where the energy comes from. Here it is from the breaking of some nuclei, whereas in other type of power plants, it is from burning something or from the power of water flowing due to gravity. So fission is the main type of nuclear reaction that we do here on Earth. There is also fusion, which is the inverse. Instead of starting off with heavy nuclei and breaking them into smaller parts, we start with light nuclei and merge them together into larger ones. First off, it is the process that goes on inside of stars. The reason why stars are bright, why they emit light, emit energy around them, is because inside of them, at their core, is a continuously going fusion reaction. Here in our sun, for instance, hydrogen is continuously being fused into helium. And this reaction creates a lot of energy, which then we're radiated outside. It takes a lot of time for the energy to actually make it to the surface of the sun. So you need. This is one of the difficulty why we have trouble mastering fusion here on Earth. You need to have a tremendous temperature to keep everything confined together. So you need a very large amount of energy that does not go outside easily. So inside of the sun, this is the case. Here, a bit harder to attain, and the energy has to make its way to the surface, being absorbed, emitted by all the particles inside of the sun. So it might take a few millions of years for the energy after being produced inside of the sun to be radiated outwards, and it makes our way towards us. Our sun is a very light star, so all it can do is fuse hydrogen together. It is not large enough to have the conditions needed to fuse larger atoms together. Even helium, it cannot merge, it cannot fuse into larger ones. So once its hydrogen supply starts running low, it won't be able to keep shining and will die off. I'll have a few another slide in which I'll have a few more things to discuss on this. For now, another thing based on this. Power plants based on fusion, like I said, are hard to do. You have to, in order to fuse nuclei together, you need a large amount of energy in general to start off the reaction. Since you need to keep all of the positively charged nuclei close together, which is very hard to do, you need a very good insulation for the energy not to just radiate outwards and you lose it instantly. So we're still having trouble with this, which is why we don't have a reliable fusion-based power plant which can produce energy without needing at least as much in the beginning. And fusion is used in the second generation of atomic bombs, hydrogen bombs. Again, since this is a fusion-based reaction, we generally need a very large amount of energy to start the reaction, which is why inside each of these is a small fission-based atomic bomb, whose sole goal is to provide the necessary energy to start up the reaction and make fusion start. But again, a lot more powerful than a traditional fission bomb. Again, in the study guide, I sent you two links. One with an atomic cannon developed by the Americans, shooting off fission bombs with, I think it was 2 kilotons of TNT, I think. And the second, the most powerful explosive developed on Earth, the Tsar Bomba, developed by the Russians, which is a fusion-based bomb, which was, if I recall, 5,000 times as powerful as a fission-based bomb. So we gain a lot more power, but it is difficult to attain due to the conditions. And to see where these two types are possible, we'll go back to the graph we had of the energy, the binding energy per nucleon, which tells us how stable a given nucleus is per nucleon, how strongly they are bound to each other. So in general, fission will tend to be viable when you start at a given nucleus, you break it into smaller parts, you end up with something that is more stable. So fission is viable in this part of the graph, which is why we use it for with uranium 235, breaking down into smaller parts. We can get energy out of it because we end up with something more stable at the end. While fusion is viable here in this part of the graph. So with hydrogen, like in our sun, and some other pretty light nuclei, up to iron 56 approximately. I said earlier that fusion was the process going on inside of stars. In heavier stars, some other fusion processes are possible. For instance, it could be possible to fuse helium into other elements. All of the elements around you, so all of the organic ones, nitrogen, oxygen, carbon, and so on, all of the others, up to iron, have been produced inside of stars to produce energy. Which is why some physicists have been known, I think Carl Sagan and Hubert Reeves have both said it. They stated that we are stardust, since every atom that composes your body, every atom that composes everything around you, has been produced at some time or another inside of a star. Past this point, it is still possible to keep producing some atoms through fusion, though you lose energy through it. So they generally are not as abundant, not as easily come by. Past iron, you do not get energy out of it. I believe this is all I had to say on this. So fission, you break large nuclei into smaller ones. You can make an ordinary fission bomb out of it or a power plant. While for fusion, it is the process going on inside of stars and what is used in the second generation of atomic bombs. On this, would you have some questions, some comments, anything? Otherwise, that is all I had to bring for today. Again, I highly recommend you go and check out the videos I put up in the study guide. They're really worth it. Otherwise, I'll be available on Zoom approximately from in 5 minutes uh, up to 15 to 10, and otherwise I'll be available today, as stated, from 1 to 2. I'll see you next time. Thank you for coming.